All right. Lecture 3 is about chapter 2. It's all about displaying data. All right. I will remind you of our spectrum for displaying data. Displaying or looking at data. Over here on the left, we've got high detail, but low speed of understanding. Does anyone remember which way of looking at data gives us high detail but low speed of understanding? This side, yeah. And which of the ways we can look at data? Talk about with your neighbor. See if you can remember. What's looking at data? Which way for looking at data do we have high detail but low speed of understanding? Raw data, exactly. When you first accessed the data for your labs, and you just saw that table of data, that's the raw data there. Lots of detail, takes a long time to understand that system. Way over here on the other side, we have low detail, but fast speed of understanding. And which way can we look at data to have low detail but fast speed? Summary statistics, exactly. So one number or a small set of numbers that describe the system. And just by looking at those 1 to 3 numbers, you can get a quick understanding of what's going on, even if it's not a lot of detail. And then here in the middle, where it's moderate detail and moderate speed of understanding, a whole bunch of different visuals, exactly. And there are visuals that are closer to the left side of the spectrum. There are visuals that are closer to the right side of the spectrum. So I'm not going to talk about raw data in this section because basically that's it. It's the raw data and you look at it and you try to understand it. We're going to be focusing on visuals and summary statistics. And let's start with visuals. Types of visuals. Well, we also have to go an extra step and say, what type of data are we looking at? Quantitative data or qualitative? So let's look at types of visuals for qualitative or categorical data. We're going to talk mostly about 2 types. One, I guess technically 3, but one of them's a subtype. One is a frequency table. And then underneath that, we can look at a relative frequency table. And then the other is a bar graph, also known sometimes as a bar chart or a bar plot. The operative word here is the bar, although some other people call them column graphs, column plots, and column charts. So let's do an example. Let's start with some raw data. Main color on top article of clothing. I'm probably just going to make up this data rather than ask us to all go around. The raw data would just be a list of the different colors I see. Black, black, gray, blue, black, red, blue, black, white, red, black, blue, Not a lot of data, so fairly quick understanding even looking at raw data. That's our raw data. Even if you don't have exactly the same written down as me, that's okay, because I just made it up anyway. So let's organize this data in a visual that'll increase our speed of understanding a little bit with the frequency table. A frequency table has two columns. The first column is the category, and the second column is the number of observations. Are there more red shirts or blue shirts? I heard blue, it took 5 seconds. Now let's make a frequency table. First column is the color. Second column is the number of observations. So I've got black as a color. And I have 1, 2, 3, 4, 5. I have gray as a color. And I have 1. Yep. I have blue as a color. I have 1, 2, 3, 4. I have red as a color. I have 1, 2. White, there's 1. And green, there's 1. Are there more black shirts or blue shirts? Black. That only took 2 seconds. And that, it took a little time to sink in what the question was. Faster understanding. Instead of having to go down the list and count, you just look at the table and 5 is a bigger number than 4. There are more black than there are blue. Now I only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 observations total, which by the way is a really good thing to have in a frequency table. Just barely fit. But if I had 100 observations, it would take a lot longer to decide which was most observed, right, from the raw data, but not really any longer from the table. Would you agree that main color on top article of clothing is categorical? Is it labels or is it ordinal? Why do you say labels, Hadley? Yeah, there's no numerical content whatsoever. Black is not more of a color than blue. Red is not 3 times green. That doesn't mean that counting is not possible, right? We can count them, that's numerical information, but the data itself has no numerical content. We could organize this in a number of different ways. I organized this by the first entry was just whatever I saw first. Nothing wrong with doing it that way. You could also organize it alphabetically, or you could organize it in terms of most frequent observation, which is often how we do it, right? So we would often sort this and have black, then blue, then red, then I'll do gray because gray comes before green alphabetically, and white. And then the total at the bottom. And that can speed up understanding even more. But the only difference is we sorted based on the number of observations. It's the same table. And that's how you make a frequency table. You did this on last Thursday if you counted the number of cities per continent, or the number of patients per age group, or the number of employees per job type. What you produced was a frequency table. And that gives you some understanding of the data that you're looking at. Is Africa well represented or underrepresented? Are the age groups equally distributed, or is there one age group with a lot more observations than the other? What's the most common job type in the tech industry, right? These things go pretty quickly when you have it organized in a table. Anybody have questions about frequency table? Okay. If we want a slightly different look at the table, instead of frequencies, we can look at proportions. But the table that shows proportions is generally called a relative frequency table. To build a relative frequency table, you have two columns. First column is a category. Second column is the proportion of observations instead of the number of observations. Or if you want to calculate it, it's the number of observations divided by the total observations. If you've taken Math 105 before this class, I'm pretty sure that you've done this sort of piece, right? It basically says, instead of saying there are 5 black shirts, we say 5 out of the 14 are black shirts. So let's do it with our example. We have the color and then the proportion of observations. I'll do it with my sorted table: black, blue, red, gray, green, white, and then I'll have a total. And it's as simple as taking how many observations and dividing it by the total, 5/14. That's it. It's a fraction, but that's fine. Nothing wrong with giving proportions as fractions. Often we write them as decimals. So you can come over and you can calculate 5/14 is about 0.36. 4/14 for the blue is 0.29 about. Then we had 2/14, and that's about, I should know these, but I'm tired, 0.14, and then 1/14 for each of the rest. .07. What does the total add to? 1, yeah, 100% or 1. The total should always add to 1. Because it includes every observation. Relative frequency total always equals 1.00 or something really close to it, right? If we're doing some rounding. If we actually added all these up, I think we'd be off by 0.01, but we're pretty close. 0.02. You might ask why you would want a relative frequency table instead of a frequency table. And the answer is partially it depends on what you want to use it for. If you want to know the actual numbers, then a frequency table is helpful. If you care more about the proportions, then a relative frequency table is helpful. If I had 683,212 observations, knowing the specific number in each category would probably be overwhelming. A big enough sample, you're probably good with just proportions instead of specific numbers. So relative frequency tables are more useful generally for large data sets, where looking at a whole bunch of large numbers can get overwhelming. Oh, sorry, we'll move that back into view. So in terms of where we are on our spectrum, from raw data to summary statistics, I would say that frequency tables and relative frequency tables are fairly high detail still. And there's another visual for categorical data that is often a little less detailed, but a little faster to understand, and that's the bar graph. A bar graph plots the frequencies of observations as the height of the bars. So we would come over here and we would say, using again our same example, we would say the frequency of the observation is on the vertical axis, and the categories are these different categories here: black, blue, red, gray, green, white, and then the height of the observation, or the number of observations, is the height of the bar. And we would call this a frequency bar plot. It's very common to care about your order for bar plots. And it's typical to have the most common observation first and going down from there when you're doing a frequency bar plot. It doesn't have to be that. It could be alphabetical. If these were years, then I could go from the earliest year to the latest year. Right? But if you're just looking at purely categorical data, it's most common to have the most frequent observation first and then go down from there. Yeah.
Could we put like the numbers of the frequencies on the left side of the bar, or is it okay to just kind of like make up how high the bar should be?
That's great. I neglected to complete. You should have your units here. Sure, that's what you're asking. And even better is go ahead and write the frequency at the top of the bar. Why not? Make it even easier for the person If they want to know that red is twice as much as gray, they can look at it. But if they want to know the exact answer, they have that there as well. Yeah. So this is a pretty darn good done by hand bar plot, one that includes labels on the bars and definitely includes units on the vertical axis. You will be producing this in your lab. It should produce it with labels. Some of the pictures, it's going to cut up the top label. That you don't have to worry about. That's not something you have to fix. It takes changing the code, and I'm not going to worry about that. Right? That's an example of some of your visuals don't always look super great, but that's okay. There are some other visuals for categorical data. The big one is the pie chart or the ring plot. I'm not going to go into it here. I don't think it always has a lot of value other than it can look a little less boring than a frequency bar plot. But let's just mention them real quickly. 3 other types of visuals for categorical data. There's the other orientation, I guess. Other orientation or a bar chart or a bar. What did I call that? A bar plot. And that basically just switches. So where you put the categories on the vertical axis, I'm just going to do 4 because I ran out of space. And the frequency on the vertical. This can be valuable, especially if you have really long names, right? If you think back to, or if you look back at this visual here, I barely got the black, blue, red, gray, green, white in there. And those like were 5 letters or less. But if you're doing racial or ethnic groups, which you do a lot of, those are categorical. The census has a category Native American or Alaska Native. It's a long title, and unless you're fine just chopping that short, which probably shouldn't be, it's easier to put it this way on a horizontal axis. But other than that, it's really the exact same. And you just make your bar, and it comes out sideways this time. One. And then you can also do a pie chart. This is often for relative frequencies. It can be just for plain frequencies as well. So you draw yourself a nice big pie. And then you take your relative frequencies, which I have here. We got about 0.36 is black. Another 0.29 is blue. 0.14 was red. And then each of these, red, I can put it in there. And then gray, green, white. And I hope you can see one of the limitations. Yeah. Sure. Like so? Yeah. I hope you can see one of the limitations with a pie chart is it can be really hard to get your information in there. And we only had 6 categories. If you have 10 categories and a bunch of them are 1% or less, you got a whole bunch of stuff just stacked up here that's really hard to see. I'm not a big fan of pie charts. It also substitutes area for linear distance. So it can make the black wedge look bigger than it actually is compared to the white wedge. just because when people think in area, they think differently than when they think in distance. So if you really like the circular effect, you can do a ring chart or a ring plot, which is instead of drawing a whole pie, you just draw a ring and then you split it into your different categories. So black, blue, red, gray, green, and white. And then you can put the proportions as well. If you're picking one of these three types, it's not necessarily wrong, but you're picking based on some sort of aesthetic value instead of like a specifically statistical understanding that reason. And that's fine because statistics is a human science and you have to know how to communicate to other people, right? And so some other people, you may say, well, they're not going to want to read a bunch of long vertical words. So I'm going to write my titles horizontally, and that forces me to use this. Or let's mix it up and throw a circle in. So it's not just a whole bunch of bars, because that can be overwhelming, right? So there can be good aesthetic reasons to choose another visual, but in terms of different sorts of in terms of looking at the data in a different way, it's the exact same as a basic frequency bar plot. So your labs, you won't do any of these. You're just going to do a basic frequency bar plot, which is fine. Anybody have questions about that? All right, let's talk. We're going to come back to visuals on Thursday when we talk about quantitative data, but let's talk about the very few summary statistics for qualitative data. So we're back here now, going from raw data. Here's our tables. Here's our bar plots. Uh-oh. Oh, good, I am recording. And here's our summary statistics. All right, for let's say categorical or qualitative data. And we're going to talk about two different types of summary statistics for categorical data. The first is specific to binary data. Remember, a binary data has only two options, e.g., yes or no, and it's often coded as 0 or 1. Doesn't mean it is 0 or 1, but it's often coded that way. And so the summary statistic, the main summary statistic for binary data is the proportion. So for example, have you taken Math 111Z? And maybe you have yes, no, yes, yes, no, yes, no, no, yes, no, yes, 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 no. And if you come up with a different set, it doesn't have to match mine perfectly. So I can make a frequency table. Let's see. We'll put the outcome here and the number of observations there. Your answer could be yes. Your answer could be no. 1, 2, 3, 4, 8. There's 8 yeses. 6 no's. And the total is 14. And so our summary statistic would be the proportion of yeses, which is 8 over 14, or about 0.57. And the P, excuse me, in statistics, statisticians just love shortening from words to single letters, whether they're in English or Greek. The single letter for proportion is the letter P. So P equals 0.57. That is a summary statistic right there. So without looking at the data at all, you can say about 57% of students have taken Math 111. That's a pretty good understanding. It happens very, very quickly. Now, you don't know what students are they. You don't know if Joey has taken it or if Katya has taken it. But you know, overall, 57% of students have taken it. And the main reason we code as yeses or nos, let me recode these y's and n's to be ones and zeros. Y is 1, n is 0. 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0. Then the proportion P is simply add everything up, divide by the total number. All right, because it's a yes, you get a 1, a 0, you get a no. So when you add everything up, you're going to get 8 ones and 6 zeros. 8 ones, ones, and 6 zeros. When you add those together, you get 8. And so you just take the 8 over 14, which is 0.57. So that's the main reason we code binary data as zeros and ones, is it makes it really quick to calculate the proportion. And this can be true, false, pass, fail, has diabetes, does not have diabetes, is in the Western Hemisphere, is not in the Western Hemisphere, is taller than 57 inches, is shorter than 57 inches. You can turn almost any question into a binary data just by phrasing it as a yes or no question. Okay. Chapter 4 in both textbooks covers binary data a little more closely and looks at some of the mathematics behind this binary data. So we'll come back to that in chapter 4. Let me talk to you about the last summary statistic that we'll talk about today, which is a measure of center for categorical data. Measures of center are super important for quantitative data. For categorical data, it doesn't really make sense. All right, if I ask you which color is closest to the center, is it black or blue or red or gray or green or white? That question doesn't make any sense. What color is closest to the center? But if I change that question a little bit to be, what color am I most likely to observe? These two questions are actually very similar for quantitative data. And so we use a similar question, what color am I most likely to observe for categorical data? Well, we had our frequency table, which I'm happy to draw again. We had our color here and a number of observations. Black, blue, red, gray, green, white. I'm drawing it again, but my handwriting is getting successively worse. 5, 4, 2, 1, 1, 1. In total, 14. So if you walked into this room, close your eyes, and swung your finger around until you pointed at someone, what color do you think you'd be most likely to observe? And why do you say black? Because it has the most observations, right? So black is the color that you're most likely to observe simply because it has the most observations. Our statistical term for the category with the most observations is called the mode. The mode is the category with the most observations. Because the category with the most observations is the one you're most likely to observe without any other knowledge about the system. When we talk about quantitative data, we'll have two other M's. We'll have the mean and the median. Those do not make sense for categorical data. And the mode doesn't really make sense for quantitative data. And we'll talk about why. But there you have it. When you're working with categorical data, you can look at the raw data for a lot of detail, but slow understanding. Or you can make a visual to speed up your understanding. We know that black is the most observed. In fact, there are 5 black shirts. We have some other types of visuals that we could use that change the way we understand it. If you're a more visual thinker, this can be really helpful. And again, with super large numbers, it might be easier with bars than with the numbers themselves. And if we really want to speed up our understanding, we can switch to summary statistics. Black is the most common. If that's all I tell you about what shirts are in the room, you have a decent idea of what you're most likely to expect, but you have no detail about what the other shirts are. All right, what other shirts are in the room? We don't know. We just know that black is the most common. All right, so the rest of the day today, we will work on the lab.